Okay, so let's do, okay. First, our first problem is we have this loop thing, and here at this point P is the spring, and the mass on the loop with mass M, of course, goes from point A down to point B here, and it just barely loses contact at the bottom. So then this is R, and so we want to find this distance D such that this scenario takes place. Okay, so then well, the first thing we do is just to apply conservation of energy. So at the beginning, when the spring is here, the energy is 1/2 K times R minus E squared. This is the energy from the spring, and plus mgr. This is the gravitational potential energy. If we measure from the center, if we take the center as the ground. And then when the spring is at the bottom of the circle here, then it's just 1/2 K times R plus D squared. Again, because the spring is stretched by a length of R plus D. And then minus mgr. And then we still have to add the kinetic energy, which is 1/2 mv squared. Okay, so that's one equation. And then our second equation is at the bottom of this loop. We can add all the forces on it to find the acceleration. Well, one force is from the spring. That's obviously just K times R plus D, and that goes up. Another force is gravity minus mg, because that goes down. And then the normal force from the loop thing, but since we know that it just barely loses contact there, that force is 0, so we don't need to consider that. This has to be equal to the force, which since it's circular motion, then it's just mv squared over r. Okay, so now we can just solve these two equations. The first equation, we can get that 1/2 mv squared is equal to 1/2 K times R minus D squared minus R plus D squared, then plus 2 times mgr. So then this is equal to 1/2 K times negative 4RD. Yeah, plus 2 mgr. So then mv squared is obviously just equal to 4 mgr minus 4 krd. So now we can just plug this value for mv squared into the second equation, and we get k r plus kd minus mg is equal to 4 mg minus 4 kd. So this means that 5 kd is equal to 5 mg minus kr. So then it's pretty easy to see that d is equal to mg mg over k minus kr minus just r actually, minus r over 5. So that's the answer to the first problem. So yeah, it's not that hard of a problem, but it's just writing the original equations can be a bit difficult though. So does anyone have any questions about this problem? Okay, if not, then I'll just do the second problem then, which is we have these two containers of equal volume V, and they have different temperatures and pressures. And they're connected by this pinhole tube. And so we want to find P1 over P2 as a function of T1 and T2. Okay, so first to do this problem, we can recognize that in a time delta T, then 1/2 of the molecules will 1/2 of the molecules within the distance V times T, V times delta T will enter the pinhole. You can see for yourself why this is true. And it like makes sense because they in this situation the molecules only go two directions, which is to the left or to the right, and so obviously so then there's just a 1/2 chance that these molecules within this distance will enter the pinhole. So then the number of molecules would just be 1/2 times, so the density of the molecules, this is n is the total number of molecules over the volume V. This is like the number density of the molecules. So 1/2 of this times the distance V times delta T. And then multiplied by the area. So this is the number of molecules that'll enter during this time, as you can see. So then we can write per unit of time, this, let's call it C, is just equal to 1/2 times N over V times A, N times V. And then since there are these two separate containers, for the I container would be Ci is equal to 1/2 Ni over V times A, then times Vi. Okay, so then we can now use the energy. So since these molecules are moving at speed v, then 1/2 mv squared, this is the energy. 1/2 mvi squared is equal to 1/2 kb times ti. This is another expression for the energy of these molecules. So then this means that Vi is equal to 1/2 times kb ti over m. Okay, so then going back to our this C, we have Ci is equal to 1/2 times Ni over V times A, and then times this Vi, which would be Kb times Ti over M. So then this Ni over V, we can't really, we don't really have a way, well, we don't really have a way to find Pi over P1 over P2 yet, because like it doesn't appear here, but then we can recognize from the ideal gas law that Ni over V is actually just equal to Pi over Kb times Ti. So then obviously now we can find an expression involving P and T. So we get that this Ci would be equal to 1/2 times Pi over KBTi times A, and then multiplied by this KBTi over M. And at equilibrium, since at equilibrium, which is the state we're trying to find the P1 over P2 for, then C1 would be equal to C2. There's no more movement between the two containers. So then this just means that P1 over KB times T1 times KB T1 over M is equal to P2 over KB times T2 over KB over times T2 over M. So then we can see that some stuff obviously cancels. These KBs and M's all cancel out. So this just gives us that P1 over P2 is equal to square root of T1 over T2. So that is the answer for the second problem. Okay, does anyone have any questions about this problem? Okay, so since it appears that no one has any questions, then yeah, then I'm that's it for me.